I think, well, I think the history of neutrino physics is beautiful, and not only is beautiful, but it's interesting. And I really think that, I think it's important to think about history. I am not an historian. I like to be a physicist, but I think you can learn to do better physics if you think and meditate about what happens. And well, this is the outline of my talk. I should also say I feel a little bit inadequate for this task. It's difficult, but I feel a little bit comforted that at this conference, the topic of atmospheric neutrino is covered by others. So John will talk after me, and Kajita-san will, as an important contribution, and Christian will talk about astrophysical neutrino. And there is an intimate relation between atmospheric and astrophysical neutrino generated by cosmic rays and the history of the detection as an element in common. And I also would like to point these quite interesting posters by persons who have been involved intimately in important steps in these things. John Loseco and Francesco Ronga. I'm very glad. I really recommend to listen to this analysis of the macro data. And of course, there is also Igor Zeleznik. Now, well, let's start. We know the cosmic rays started in 1912, and we have celebrated the things, and we know, and particle physics was born together with the discovery of cosmic rays. So, and very quickly, you know that you discover the positron, the muon, the pion, the kaons, and so the things clarify. I'll jump over this fantastic history. And let's say, so actually it's really interesting. People understand electromagnetism, electromagnetic shower, and then they also understand hadronic showers, how they're developed, and they understand they're pions, pion became muons, and then there is neutrino. And so let's get, this is July 1952, and there is this is a review of modern physics by these authors. There is Ken Greisen, Cocconi, and this is actually a measurement. You see, this is data. This is the vertical muon intensity. Already in 1952, the muon spectrum had been measured, up to, this is 2 kilometers of water. And actually, it's interesting that in this paper, they also reconstruct the cosmic ray spectrum. So they understand, these people understand how to make hadronic showers, and to make muons. And this is actually remarkable. And while, of course, there are also extensive shower array who measure the cosmic rays. And so they understand muon propagation. They have models for particle production, and they're capable to calculate the muon spectrum. It's a really remarkable result. Actually, it's interesting that in these reviews of modern physics, there is not the word neutrino. But of course, this, I'm assuming you all know this. This is in the fundamental mechanism for which in showers you generate neutrino is that you have this cosmic ray interact in the air, generate secondary particles, and then, well, you have this and the charge conjugate channel. So if you have muons, you must have neutrinos. And in fact, you must have this 2 muon neutrino to electron neutrino. Actually, the distinction between the two flavors will only be established in 1962, but anyway, you have these things. So the result is that at this point, you already know that there must be, actually for a long time, especially in the Soviet literature, people were talking about cosmic neutrino, it's a cosmic ray neutrino associated to cosmic rays. And now we more call them atmospheric neutrino. So the question is this flux detectable, and how? And of course, there is a question, the question that Francis Christian and his colleagues have given an answer recently, and the question is, are there astrophysical neutrinos? So if you generate cosmic rays, there must be high energy neutrinos that are generated. And actually, then, how do you do this? Which kind of detectors can measure the things? And actually, this is a little chapter. I think there is a beautiful history of what of the consideration were done in the Soviet Union. And so this is Markov and Pontecorvo. we started thinking already in the 50s about how to detect the things and speculate. So actually, these are some of these visionaries, dreamers, but very concrete dreams of how to do this. This is just a little bit of literature. Actually, I think I'm really glad. I don't know if Igor is here. Igor Železnik has written a quite interesting analysis of these years. Actually, it's fascinating. In 1957, you knew very little about the neutrino cross-section. So actually, this was an important point. You didn't know about inelastic neutrino cross-section and so on. You had to speculate, and we were speculating about different things. And so actually, a lot of considerations were developed in this time. And of course, Greisen, which had done the muon calculation before, also started proposing concrete proposal of how to detect this neutrino. This is an important paper in which also the basic idea of the water Cherenkov was developed later, already started. So the first detection of atmospheric neutrino was really performed using neutrino-induced muons. And so this is the idea. You have a nu mu or an anti-nu mu. It interacts outside of the detector. So this white stuff should be seen as rock. And then you have the muon, and the muon can enter, traverse the detector, or if you have a detector, it can stop in the detector. And actually, it's clear that the rate of this event can be larger because you can use the target outside the detector. And so actually, this is a plot taken from Tom Geiser, and you see relatively that if you use this technique, you select high-energy neutrino, because the more high-energy neutrino, you have a larger cross-section, and you have more target because the neutrino is more penetrating. And so actually, of course, the detector is simpler, because you do not see the interaction, but you see just a muon passing. And so this idea was developed in the 60s, and this is this important two detector who obtained the first observation of atmospheric neutrino. One detector is in India, in the Kolar Goldfield mine, and the other one is with Rhines as the main force, is in South Africa. So actually, the story starts at the beginning. This is a paper, sorry. In 62, 63, the Indians started to go very deep in the gold mine. To gold mine, people go very deep. They were going, I think, more than 3 kilometers underground. And they put this detector in different positions. And so they actually went down measuring the muon spectrum. And actually, they found that a very large, so the exponential fall was continuing. And when you were going very deep, you were not seeing things. And they wrote these results. Actually, here there is, that's a nice paper. Actually, I think William Kropp is here. But the thesis that contained these results was the thesis of Ramanamurthy. And so actually, they immediately understood that this idea to go very deep could allow the measured atmospheric neutrino. Actually, they went to India, looked at the detector, and they decided to go to South Africa for different reasons. And actually, so the idea is that the rate was very low. You had this location very deep underground. You could go deep underground, and then you could see these neutrino-induced muons. And both groups, working probably in competition at the same time, performed this result and obtained the measurement. So actually, so this is the Indian experiment. They put the detectors horizontally in order to see horizontal muons. And this is the detector in South Africa. I think this is Rhines. I forgot, I'm sorry, I didn't write the names. And so you could measure the muons. And well, anyway, I think the history of, I'm very fascinated by the ingeniousness and the courage of people who have constructed these detectors. This is, I really enjoyed reading, for example, this paper, the reminiscences of this is Case, Witterwan's Irvine atmospheric neutrino experiment. It had this fantastic history. You needed hours to reach the side of the detector. And well, anyway, sorry, I don't want to lose your time, but it's really funny. The Gogafangers were, going there and capturing this neutrino. And there was actually some amusing history how they were accused of doing nuclear research with the South Africans, and actually there was discussion at the United Nations about what the hell they were doing, so people like Grant Sasser can take. So anyway, so the idea anyway was this, that you have the exponential fall of the muons, and then you start to see the neutrino-induced muons. And so you can see at very, very large depth, at a certain point, you start seeing the result of neutrino. Another way to see it, you can see it in terms of zenith angle distribution. You see, this is in degrees, when you're very deep, you see the atmospheric ones, and then you see the atmospheric ones. So one point, and actually it's interesting, this was realized very soon. This is the first things I've seen. If you see a neutrino, and this is the problem of the up-down symmetry. If you see a neutrino which is coming of an angle theta below the neutrino enters with pi minus half theta. So in fact, when this experiment, we're not measuring the versus of the neutrino, but we're only measuring the direction. So you have an ambiguity in the angle. So they were summing the flux coming from this direction and they're coming from that direction. So in principle, you can already perform an oscillation experiment with this technique. So this, well, I'll jump over this. And they were able also to predict the zenith angle distribution of these results. Well, anyway, this, of course, there were, after the first detections, which were obtained essentially at the same time, the two papers are separated by like 10 days in the submission to physical review lectures and physics lectures, with the Kohler Gold field arriving just 10 days before. And these people try to interpret the results. Of course, in principle, if you could already make an oscillation study from these results. This, of course, was not done because you didn't know the cross-section. So actually, this is the cross-section in 1971. So these were the points that you knew at the time, which have been obtained, I think, at CERN at the time. And so the uncertainty of the cross-section was very large, and these were not allowing to perform an oscillation analysis. Well, I mean, actually, it's curious. This is from the South African experiment, in which they interpreted the results in terms of, as a limit on the W mass. And actually, curiously, they were getting both a lower limit and an upper limit. And the lower limit actually was obtained in a curious way, because there were models for which, if the W boson was very light, there was a coherent production in a very large cross-section, which is not observed. And actually, curiously, in some sense, they didn't see the W should suppress the linear increase of the cross-section. And you should mention that this experiment also were thinking about the possibility that some neutrinos are astrophysics, and in fact there are lists of events with celestial coordinates. So they were looking about this possibility. So this is a third experiment which operated more or less at the same time. The interesting idea that this is a detector with magnetized iron. So it was able to measure not only an integrated flux, but also a spectrum. Even in the spectrum, the detector obtained only 5 events, but they published a spectrum with these 5 events. And is this one, forming an integral flux. So this actually, there is a Kohler Gold field measurement and these measurements. And even there, they used the result. So actually, this is the first result which identified upgoing tracks, because they needed to identify upgoing tracks because the experiment was too shallow. And actually, they used these results to say that the W mass is larger than 10 GeV. And this is because the cross-section was not suppressed by the W propagator in the event. And actually, I would like to continue the history of passing muons. It's interesting that the Soviet Union, I'm already so late. The Soviet Union didn't have a good mine, and so they decided to build their own mine, and they constructed Baksan. And then there is macro, and this is also macro. I really recommend you to see the discussion of Ronga. So actually, here I think I'll jump this proton decay. So the interaction with proton decay in atmospheric neutrino is really fascinating. Actually, this is the first significant limit on proton decay, which is obtained by the Reines group, and you obtained it in 1954. Actually, there is a beautiful review of Goran Senjanovic about proton decay, and you say, look how it's nearly apologetic, saying, well, look, maybe we could look about proton decay. This is, of course, very soon and obtain a limit of 10 to the 21 years. And then, of course, very quickly, Reines and his group published more and more stringent models. This is already in 1967, was going to 10 to the 30 years, using the detector, which is placed deep underground. And then, then comes 73, 74, Grand Unified Theory, SU5, and then people say, I think the article of George I. Quinn and Weinberg say, we should look about, I think it was 8, 10 to the 31 as a central value. And then people went immediately to look for proton decay. Actually, both the Reines group and the Kohler group published quickly more analysis of proton decay and setting a little bit better limits on the light or the importance of the results. But then, of course, people started to build the new detectors. So there is Sudan 1, IMB, Kamiokande, and so these new detectors, designed on the basis of proton decay, started to obtain results. So actually, this is a result of NuSex. I miscalculated my time horribly, so I'll rush through this. So anyway, the anomaly. So these detectors see the events, and well, John Losecco has been followed the things very closely. So in 1986, this paper comes out, and in this paper, there is a result that there are too many muon candidates in IMB because they detect, too few, sorry, of course. And this is the key of this paper. And there will be many things to see. So you see an anomaly. The anomaly has a certain statistical significance. But the problem is, in some sense, this is absolutely correct, but it's also tautological. You see this discrepancy. So this can be, can be that you have the theory wrong. The prediction is wrong. It could be that you are doing an experimental error, or it could be that there is new physics, and you have to solve this problem. And I think the solution, how actually, Kajita-san, the title of his talk is how you pass from anomaly to evidence is the story. I think this history does not finish in 86, 87, but finish in 96 after the Super Kamiokande results, because people have not accepted these results. It's a long story. And so anyway, actually, it's interesting that somehow IMB never strongly came out in favor of a neutrino oscillation or a new physics hypothesis. But this would be a long discussion. I like John and Takahaki discussed this. Kamiokande presented the results in a more explicit form and oscillation parameters. And a theme which would be quite interesting would be the theme of the IMB and outgoing muons, which had excluded the same region where the effect was appearing. So anyway, so actually here, this actually should be the core of my talk, and understanding that I have no time. But the problem is systematic error or new physics. This was the problem. So let me just outline the problem, if this is obvious. So you see classes of neutrino events. So the classes of neutrino events come, in principle, from, this is the standard model. So all of this is the neutrino cross-section, the neutrino flux. You need the cosmic ray flux, and you need also to apply solar modulation, geomagnetic effects. Then you need to make the shower. So you need the hadronic cross-section. You make the particle decay, and you make a scheme to calculate the whole things. Then the neutrino interact, and then you have detector properties. So now if the events don't come out what you have calculated, you have two possibilities. You can put an error in some of these elements, or you can assume that neutrino propagate in a different way. And so the question is that you have to solve this problem. And I think for many years there have been intense efforts investigating all the elements of this chain in order to find if something was wrong. And eventually, this didn't happen, and you were compelled to say that there was something in neutrino propagation. So actually, I have to jump over this part. There is this very nice review of Gasser and Honda, which in some sense key authors, well, Kajita and Honda, Midorikawa, there were several groups who did this calculation, and actually it would be important to give a review to the original calculations and so on. I think there is a whole history in which the calculations were done more and more precisely, with more and more attention, and essentially the calculations were all, no significant mistake was found, and with the different elements, and I think it's interesting. I think, to me, anyway, just to make, and this remains the key uncertainty. I think the cross-section of the neutrino is now better measured, but the real problem is particle production in the atmosphere, which remains not completely known. We test with muons. I think there have been two crises in the history of atmospheric neutrino calculation. One has been the problem of polarization. So at the same point, there was understood that polarization was important. And then at a certain point, it was understood that three-dimensional calculations were important. But anyway, this continuous effort, continue to yield the same result. Okay, I just mentioned, this is a topic which is interesting. During this time, while people were trying to find the experimental error, and I imagine that in the experimental group, there must have been ferocious discussions about systematic errors. People were developing different type of models. Actually, Evgeny Akhmedov was, I think, the first one to suggest sterile neutrinos as a possibility. Okay, this, I'll take 30 seconds. I was a little bit in doubt, but I think it's important to remember the general scientific climate for this. Actually, Guido Altarelli, I'm a great admirer of Guido Altarelli. He was my professor, and I have enormous intellectual admiration for him. So this was in 1994. Actually, some of you were there. It was the Venice Telescope Conference, and he gave the first talk. And giving the first talk, I remember very clearly, he came, took a transparency of atmospheric neutrino. It was plastic time. Put the plastic there and said, look at this. I know there is this data. I know there are this anomaly, but I will ignore it. And I will ignore it because of theoretical prejudice. He said very clearly. And I said, because this will require large angles, and large angles are unpalatable. I remember this unpalatable because I say, that's an interesting word. But I think it's very serious. I don't want to criticize Altarelli, but I think the question of how a theoretical background is similar. And actually, he's not the other one. I was also at this conference. So this is John Ellis, and the same things. And actually says, I prefer to wait and see whether these claims are confirmed. Not that these people accept the solar neutrino experiment. And so there is these questions. I finished. So okay, actually, I must say, Francis Halsen was, I think I remember talking to you, Francis, in 1993 and discussing about the situation. And you were one of the first persons who told me, between solar and atmospheric, if one will survive, maybe it will be atmospheric. And I said, really? This is strange. I would say the contrary. But so some people were, well, anyway, I will jump the things. So anyway, this is, but this, I think, is sometimes is the core of this, the flesh and blood of experiments. There's been this history. This is a word which I take from this Gallison. We will hear about the saga of neutral currents. And so there was during this discussion, the alternating neutral current and these whole things. I feel that the flesh and blood of the discussion of atmospheric neutrino has been this whole history, which lasted from 86 to 96. And so the resolution of the anomaly, I think the resolution of the anomaly in this case came really from the extension of the data. so from Super Kamiokande, because the extension of the data, enlarging, L and E gave more structure, and so this and the consistency of the result. From this clearly emerged the result, and this is my personal comment. Witnessing this whole development, I think for me was not only very interesting, but gave me confidence in the scientific method, that our community is, with all problems and things, capable of extracting, or at least in many cases, the truth of nature. Okay, sorry for being too long.
Thank you for this very nice talk. What I propose is a couple of urgent questions, and then we mix with, or we go straight ahead. We go straight away to John's, and then the questions come afterwards.
Okay, well, had I the opportunity to see the previous talk, I would have eliminated most of my slides, because what I have to say is quite redundant with that. And this is a rewarming of a talk that I gave in Trieste in June, I guess it was. And I call it the saga of atmospheric neutrinos, actually. Yes. Actually, the title was suggested by Professor Smirnov back there. And I took the idea seriously that it can be, why is this not changing? Oh, there we go. A saga, yes. And I looked up the definition of a saga, a great scientific tale of persistence, dead ends, serendipitous discovery, redemption, and glory. And I think the story of atmospheric neutrinos in a minor way is So the story starts with the pioneering experiments in the gold fields in India and South Africa in the 60s, and years of struggle with small groups of the true believers who had very little support, and we weren't able to proceed until a wrong theory, SU5, was proposed in the late 70s, and we started getting money to look for proton decay, but it was not neutrinos that drove the horse, drove the carriage. But in the late 70s, about 78, 79, we started making proposals for these large underground experiments, and as you know, they were built in the US, Europe, Japan, and Russia. And by 1983, IMB, as I think John is going to talk about, had already run on to the muon neutrino anomaly. We knew it almost right from the first days of turning IMB on, but we didn't believe it. There's one thing I wanted to add to the historical record there. As part of the conservatism of the IMB group was due to the fact that there had been mistakes by some people in that group not long before, namely Fred Reines, who claimed neutrino oscillations in reactor neutrinos in 1980, I think it was, and people were very cautious about crying wolf. And by the way, one of the things in this conference I'm already seeing is a tendency to sweep under the rug the mistakes that were made and not embarrass people by talking about some of the wrong-headed things and errors that we had in the past. But that sort of disappears with time, as I'll say more about. We had the yields from these various experiments, and then the surprising 1987A distribution of the neutrinos from the supernova and the Large Magellanic Clouds came along and warmed up the low energy end of the neutrino business, and remains the only example of a supernova that we've seen in neutrinos, except maybe in some way from the ice cube results. Why are we not going ahead here? Hello? Why is this thing not advancing? There we go. So at any rate, Super K was built. Well, I need to back up a little bit. As you will hear more, the muon neutrino anomaly became a very serious issue. And what we gloss over often is that there was tremendous controversy about it. And indeed, I remember having hard words with various people. Yes, we did. We became passionate about it, John. Eventually it was sorted out, but really not sorted out until Super K was built. And then along came, of course, Snow and Camland to nail the lid on oscillations, all those previous experiments only having demonstrated the disappearance of neutrinos in various circumstances from the sun and in the cosmic rays. Okay, virtues of the atmospheric neutrinos. I think everybody knows all these things. Free, the beam is always on. The energy range is much larger than you can get at any accelerator, covering from, say, 10 MeV to 100 TeV, 7 orders of magnitude. The up-down going asymmetry, which Paolo mentioned just before, the Earth provides a variable absorber, another advantage that you choose a zenith angle and you get to filter off. It's a low-pass filter, order of 10 to the 10th grams per square centimeter. The mu to E ratio is a very reliable ratio, known extremely well, and you don't have to use any of the tricky atmospheric neutrino calculations, which are still in doubt. And it has a small but useful tau content. And of course, as we also know, atmospheric neutrino detectors can also detect accelerator beams, as they have been used for some time now. And this was just the same slide that Paolo showed earlier. So this one I wanted to point out that in the spectrum of the neutrinos, this being 1 GeV and 100 MeV, there is generally good agreement about the fluxes up at higher energies, but when you get down to the lower energies, the discrepancies in the fluxes can be very large, depending on location and other things. And so here is the ratio of muon to electron neutrinos as a function of energy. And it's, of course, because of the known kinematics of the muon, completely solid, the pion and the muon completely solid below 1 GeV, and flat, and the variation due to energy, where we don't know things as well, sets in after around 10 to 100 GeV. And this uncertainty in the low energy regime remains even today, as I will show you in a bit. And this is the same slide that Paolo showed, showing that in these underground detectors, all of them, you can select different classes of events and select different energy regimes. And the higher energy end, which is not so clean, but goes on up to the TeV regime and almost overlaps with what you'll hear about from Francis and others about the ice cube results. So you've seen, I went fast over that. You've seen this before, the two pioneering detectors. So I wanted to reinforce the first calculations by Markov and Igor Zheleznyk, who is still here, one of the great pioneers in the field, and it's really great to see him here. Kuzmin and George Zeppin and Ken Greisen and Kausik. I did not do a thorough review, but those were the pioneers. And then a little later on, then there was the English group, Wolfendale's group by and large, and some Indian friends did better calculations. But of course, they didn't have a lot to go on. The hadronic physics was not that well known. The cross-section of the W mass was not known. A lot of things. So there was a real hiatus in the neutrino business after the initial detections in Kolar goldfields in South Africa. There was a long period in which absolutely, well, not absolutely, but very little went on. Things started to stir up in the late 70s. First of all, we got going on this idea about demand, which all the older people here know about, the first notions of putting a very large detector in the deep ocean, which was originally suggested by people like Markov and Greisen and company. And that stirred up some activity, but the activity really got going after the SU5 predictions. But the 76 Duman conference, which was in Hawaii, the first major conference, was really a crucial moment in the history of the neutrino detectors, because at that conference we first sketched out the detectors that later became realized in various means, including the underground detectors for proton decay. The idea to make a detector with the optical sensors on the outside looking into the volume. We sketched out the sizes and rates for those, and of course of the larger open arrays for the water, which are now being pursued in KM3 and realized beautifully in the IceCube experiment. So the calculations, there was quite a watershed moment in '76. And then in the early 80s, the tempo picked up with the rush to construct the large detectors. Also not mentioned much is the fact that computing power had a lot to do with it. In the IMB experiment, we had our computer, which had to sort out the events online, was limited. John, was it 10K of memory in those old DEC computers? Oh, 32K. It was, what, 1,000th of what you have in your cell phone nowadays. So that really makes a big difference. Right. So this was the same flux prediction that you saw, but I will mention that one of the things, again, not mentioned very much, that frustrated us somewhat in the early days was there was a tendency for us to measure a neutrino flux or an underground rate, and then calculations to come along and verify that rate. And okay, you saw the depth and intensity. So it is also not often mentioned that the South African and the Kolar Goldfield rates were a little bit low. You know, 20/20 hindsight, we can say, well, you know, they already had a hint there. But the trouble was, none of these calculations were credible, so nobody could make anything of it. But looking back, you can see there was something going on. In the in IMB and Kamiokanda, the things strengthened with seeing that the mu to E rate was low, was smaller, that it should have been 2, around 1 or 2 GeV, and it was nearer to 1. And then there was the confusion by either no evidence from Fréjus. Fréjus collaborators often told us we had it wrong. Minnesota didn't have evidence, then did have evidence. Mont Blanc and later from others. And this became christened the neutrino anomaly, or the muon neutrino anomaly, and became for a time quite a heated debate. Kamiokanda, maybe Takaki will jump on me for this, claimed oscillations in 1990, but most dismissed them because the statistics were so poor, and only those doubts were only erased in 1998 when our very first look at the oscillations. Fitz came with something like 16 sigma the first time around. Okay. So the anomaly was there, but it was debated very heavily, and I'll just spend a few minutes when I get to it here on some of the causes of confusion. So as I say, it was first cleanly seen in the IMB detector, but we didn't make much of it. Everyone was afraid of making strong claims, except John, who believed in oscillations from the beginning, I have to say. By the end of the IMB run, we had 401 events when, with 104 with a muon decay, and the expected ratio was 34%. What we saw was 26% with errors about 1 or 2%, 3.5 sigma problem. But I think it's important for well, here are some of the other reports. The NUSEX experiment in the Mont Blanc Tunnel also had a low report. Kamiokonda reported 36% and 86. So one of the causes of confusion, not mentioned yet, is that it was and is still true that the electron neutrino rates have always been slightly under-predicted. So that our measurement, if you looked at the electron rate by itself, you would say there's more electrons than there should be here. And the muons were seeming a bit low, so it was natural at first to think about the oscillations being between nu mu and nu e. And there were those who remember there were many models of oscillations at the time, tremendous number of models, some of which I participated in. And what we were, in general, working with incorrect understanding at first, at least in the mid to late 80s. And this was the view of, Tony Mann presented this in 1990, but I think it was, yeah, that's correct, 1990. And this was the anomaly, which is the ratio of mu to E as seen in data as compared to Monte Carlo predictions. And so there, now in the case of nothing going on, whoops, nothing, back up. This thing does not back up well. Well, I guess I have to go forward. In the case of nothing going on, the ratio should be 1. The expectations to seen should be 1. But if the oscillations are going on, then different experiments could and did report different ratios of the anomaly because of their energy sensitivity range. So they shouldn't have all been the same. So there was a tendency to see the anomaly in the water detectors, but not in iron. So some people started saying, well, you know, there's something wrong with those water Cherenkov detectors. So maybe that's the problem. And that was laid to rest not until some time later when we built, the Kamiokonda, Super Kamiokonda group built a big detector at KEK and generated showers with the local beam and laid that to rest. Two cross-sections and fluxes could and were wrong. There was always the possibility of detector up to down and EMU biases. We did indeed find some and laid them to rest, but in the detector business, this is always something to watch out for. So one of the other hypotheses that was around, and I think I even contributed to some kooky models, was that there could be new sources of electron neutrinos that bumped up the electron neutrino flux, or even possibly nucleon decay producing electron neutrinos. None of those models worked very well, and they were discounted, especially when you go above 1 GeV. You could lay the proton decay source to rest. And I would say that another sociological problem was that cosmic rays did not have a great reputation. You know, the hot shots had all moved on to the accelerators by this time, and the Carlo Rubias and so on, and such like people were Sam Ting, well, Carlo, okay, Carlo, but Carlo screwed up the one in HBW, for which is not remembered so much, that while he was winning the Nobel Prize in CERN, he was not winning one in Utah. So there was also, for instance, not mentioned here, Saburo Miyake, a wonderful friend of mine, now not seen around. I don't even know if he's still with us, but he's disappeared from the scene for a long time. Saburo regularly made claims at conferences of having seen proton decay in the Kohler Goldfields experiments. And we would have big shouting match fights, but amongst friends. It was great, but he did think they'd seen proton decay down there. It wasn't taken seriously very widely. Right, and then IMB published an ill-considered paper by one particular student, and we let it go by. Yes, don't need to say who. It wasn't me. It wasn't John. So, rejecting oscillations down near the regime. It was done with the exiting events in the stopping muons, where there's a real problem with understanding exactly what are entering events and not. A long story. Early claims from Kamiokanda were not so strong, and the delta M squared they got in their early claims was very much too high. And something I've never understood, many people made some claims early on of seeing oscillations, but they always got a delta M squared up in the range of around 1 EV squared, not lower. There was a tendency with lower statistics to drive the delta M squared solution high. But at any rate, things only clarified in 1998 when we published the now famous paper, which, by the way, was only the discovery of muon neutrino disappearance, not neutrino oscillations, as we would like to say, sometimes do say. Yes, as I said, starting in the 50s, particle physics progress began to shift toward accelerators, and the ICRC became somewhat staid. I used to go to those meetings and see my old friends from years before. Yes, I got one more event, by golly. And we'd have big discussions about that. But it was a slower and more pleasant climate, I must say. The alligators were all at the accelerators. Yes, the quantities like the input cosmic ray fluxes were only good to 10 or 20% or even worse, and that was a problem. And of course, the W mass not known until '83, and we couldn't do fancy computer simulations. We all take for granted until the early '80s, and really not well until the '90s. And, I had that little propaganda point in there that the non-accelerator experiments have led the way in discoveries in particle physics, except for the Higgs. But the Higgs, that was a foregone conclusion. So this was supposed to be the yellow brick road, and it's something I like to talk about with the students, which is that in teaching the history of science, we tend to teach the yellow brick road. You just follow the yellow brick road, it'll lead you there to nirvana eventually. But of course, real science, for those of us who've been around for a while, ain't that way. What happens is there are side roads, dead ends, there's sometimes dragons along the way and so on. But it's not nearly the way we tend to teach it as this logical step leading to the next and so on, and eventually reaching some truth. The miracle is that I think in general we do reach something that we can say is scientific truth, and not for the historians, not a construction of social theorizing. That fortunately, the postmodern theorists have mostly gone away. They don't bother us much these days. But there are many cases here where things we got wrong. I just mentioned one, Sandeep Pakvasa, who many of you know, and we love vacuum neutrino oscillations, and we wrote papers about that. We were so many orders of magnitude wrong, but it was an aesthetically pleasing result. And it was only Atsudo Suzuki's gamble to build the Camelan detector at the location that it is, that paid off. It could have easily seen nothing. If the vacuum solutions had been correct, that experiment would have been a dud for observing neutrino oscillations. So Atsudo deserves more credit, I think, than he has gotten. And there are many times that we've been fooled by the neutrinos. Well, I guess the message of my talk, I'm going to have to quit, but oops, can I back up? The message of my talk is that in real life that things are not at all clear, and this is really something we should all emphasize to our students. These controversies that are emerging and so on. When you're in the thick of it, nobody really knows what is going on, and you have to keep an open mind to all kinds of possibilities. So this was just an old table I used to show in the early 90s about all the possible solutions to the neutrino anomaly. Oh yes, just one to say how the gods have smiled upon us. You know, there are many of these things that are so, there are many of these things that we've been so lucky about. The fact that the atmospheric neutrino oscillations length at the typical cosmic ray energy of a couple of GeV is about a chord of the Earth was really fantastic, that it divides the data sample into no oscillations and oscillations. That the mixing angle for nu mu nu tau is near 45 degrees. That the 4 MeV neutrino oscillation lengths are 2 kilometers and 150 kilometers. Nice terrestrial distances. And that the Wolfenstein matter effect distance is just about the radius of the Earth. No good reason for that. I think Professor Smirnov is going to talk about MSW in the sun, which I think most physicists don't really understand that what's going on there. It's not what you think. I'll just say, this was already said, the atmospheric neutrino calculations are very hard. There are things that are still around. The quark distributions at X going to 1 are not well known. The K to pi ratio is still ambiguous in the very forward direction. Right. So there's as Paolo already said, there are many things that go into that soup. And that soup is not that well determined even now. I note also, Francis maybe will mention this, that direct production, which is to say production of some heavy quark states that decay and give you neutrinos in a short distance from the atmosphere and should be isotropic, they're still not discerned in the cosmic rays, and that's been something we've looked for a long time. The mass order is not settled. CP violation, I've slipped in the snotty remark about who really cares. Majorana or Dirac, and of course we know that every red-blooded theoretician likes Majorana neutrinos, but maybe they're Dirac particles like all the others we've seen. So this one is one people don't often remark on, which is that there is still a deficit of, an excess of neutrinos compared to calculations, both from the atmospheric neutrinos and in the calculations at accelerators. I think progress has been made with tuning up for Dune and so on in recent times. But it's always been the case in Super K that we normalize the data basically to the electron neutrino flux. And it used to be a 20% discrepancy. Here it is, 14.3 with the normalization, and it's actually a little more than that because of all the other fiddling around with normalizations. So there is maybe something going on there that we haven't yet untangled. So I just said all of this. Yeah. Okay, we're still waiting for the next supernova. So I think this one may be answered. Where are the Glasgow resonances? Maybe Francis has one now. Or, I'm sorry, right. But we don't have any of the BZ, or usually, it should be Berezinski-Zatsepin neutrinos, not GZK as most people say, because Berezinski and Zatsepin were the ones that recognized that neutrinos would be produced in the GZK cutoff regime, inevitably. But we haven't seen those yet. The reactor neutrino anomaly can talk all day about that. And the mini boon business, certainly something curious going on there. The neutron lifetime enigmas and speculation. This is, I think, pretty well dying, the idea that there might be dark matter and a neutron decaying to a slightly less massive dark matter particle. But I think it's not ruled out yet. Yeah, dark matter balls coming in, which could explain the mystery of solar corona heating. It's a nice idea, but there's some evidence against that. Christian is smiling. And Anita has two events, in case you didn't know, that are coming up at 30 degrees out of the ground, where there should be at this energy, which is 500 PeV, should be no, I've forgotten what, e to the minus 50 transmission through the Earth. If they find more of those, it's a real problem. I think they're going to find a problem with the experiment, but they have done very close checking. So there's a lot of things out there. Yeah, not even a hint of PDK. That's, you know, that's a kind of reassuring in a way that the social invention of knowledge doesn't always work. We haven't found proton decay despite looking for it everywhere. You can't just manufacture it because you like to find it. Okay, many thanks to the organizers. I look forward to the rest of the week. Let's get coffee.
I have three comments. I guess I'm allowed to do that because there were several speakers. The first one is for Paolo. Paolo, it was a great talk, but you really needed much more time, obviously. When you said at the end that there were no mistakes in the atmospheric neutrino calculations, you were being kind. Because as you know, in 1996, it was found that there were mistakes in the Lee and coflux, and that had some consequence. There were mistakes found in the Lee and coflux, the first 3D flux calculations, and this was published in Phys.Rev Letter in a paper comparing all of the fluxes. Turns out that had some significance, not so much for the discovery here, but it had significance later on for IMB3. And I had very little to do with this decision, but I have records, emails, and so forth, showing the reason why IMB3 adopted the Lee and coflux was because we didn't know it was wrong, but it agreed with the data better than the other flux calculations. So people do strange things without knowing why. So we were using a wrong flux, and no one worried about why it was wrong because it agreed with the data better. It didn't really agree with the data, but it was a little bit better. Okay. Now a question for John, or a comment he should have made in his talk, but he didn't. John, the performance of IMB's response to muons was known very, very well from stopping muons in the detector. We had an excellent source to calibrate the muon response. So in fact, we understood it much better than you might think, because we had a very good sample available of things that we knew were muons because they got that far underground. So there's a little bit of that story where
yes, but everybody was very nervous. Maybe we've screwed up the calculation somehow, some mistake in our calibrations of our mu decay detection efficiency.
But as I say, we had an experimental number there.
Right, but
It wasn't just a rough calculation. We had real data, and you could tell they were muons because they had the detector.
I would have a question for two IMB collaborators. So really, the stopping muons, do you understand now? Because that was really an explicit contradiction. You had the region which now we know, essentially, oscillations are there, was excluded a 90% confidence level, really that region. My understanding was that perhaps was a cross-section problem. You think
No,
it was an
no,
acceptance?
that's a different question. Well, by stopping muons, I mean stopping as atmospheric cosmic ray muons that penetrate to the detector.
Oh.
What you're thinking about are upward-going muons, which are neutrino-induced, different physics, yeah.
These were
One was very well
contained
understood.
interactions where we had the stopping
Yeah.
muon.
Okay, well, I was talking about,
Yeah, you're talking about something different.
And finally, and this is something that's really hard to talk about, there were some threats and intimidation in IMB, including, for example, my postdoc, Bruce Cortez, was forced to resign from the experiment. So there were some really strange things going on back in those days, and we really don't like to talk about them, but it was not so much
Other
fun.
things there that we wouldn't want to talk about, John.
We're supposed to be, we had confidential agreements then, so.
Sorry. Actually, I have something which is not within that discussion now. Also, Christian Spiering, DESI. It's a historical curiosity. Heisenberg was the first who mentioned atmospheric neutrinos in 36. And he said that small showers generated by neutrinos, by Pauli's neutrinos in the atmosphere, would sustain the showers. For that, he had to assume a ridiculously high cross-section. Of course, that was 2 years before Bethe and Pius calculated the cross-section, but there is this paper.
So, hi. Okay. Hey, John. I have a slightly off question. The Americans really, IMB was a pioneer in that field of the giant water Cherenkov detectors. Why did you stop?
They wouldn't give us any more money.
What?
The funding agencies, after Supernova 1987A, the DOE said, well, you've done your thing, you're finished.
No.
Huh? Well, there was a leak. There was a leak that could have been repaired. It's not that big a deal. But the DOE said, you've done your thing, it's all over. And it was,
And there was
it's the DOE's attitude at that time, and it is today, that the idea, let me just tell a little story. I went to the defense of Super K with Totsuka in Japan, being with a panel of august Japanese physicists. And at the end, they said, Professor Totsuka, how long do you plan to run this experiment? And he says, 100 years. Afterwards, I said, Yoji, what the hell are you saying, 100 years? He says, I won't be here. But there's a difference in attitude. And, the DOE is the American business style. You take your profits and move on. And we've never managed to conquer that. The idea of having an observatory in particle physics taking data for many years. And of course, it's in the comparison with accelerator experiments, where it costs you an astounding amount to run the beam and keep running it forever, whereas it doesn't cost so much to run an underground observatory.
so there was a convincing, I think there was really an effort to make Super IMB in the US, or not really? Because you didn't give up, you went to Japan.
Yeah, that was what we did.
But did you try, was really the funding agency who refused to fund a super,
we-
because it's a very, very natural idea. It was nearly unavoidable. You had to do,
I can tell you, it was my student, Steve Dye, who had worked on IMB, and he called up the Japanese and said, would you like to collaborate? And then eventually it went from there, because we knew we would not get the money in the US.
Just
To contribute something to that, and again, this is primarily opinion, I think there was some sort of quid pro quo associated with the SSC, which was a very high priority in the
Well,
US.
yes.
And this was sort of a contribution to the Japanese to keep them involved in the SSC. So you again have to go back to what else was going on at that time.
Well, the U.S., remember, contributed 6% to the Super K effort, so a negligible amount.
One point, you're not reading the right literature if you say the social constructivists are gone.
We wish they were gone.
That, but wishing doesn't make it so. You know,
That's what they say.
Actually, I think depending on who you read, although I have opposed them at some length, wasting a lot of paper, not everything they say is worthless. Some of it is quite valuable.
No doubt, no doubt.
And also, in defense of the textbook writers, their job is not to give the history of physics. And I say this as someone who's written an article, physics textbooks don't tell the truth. And how many physics teachers are prepared to
Right.
discuss the
Absolutely.
actual history of physics?
That's right. That's why it obliges us to try to put a little hair on the descriptions of the evolution of some of these things, which we generally don't have the time or space to do.
Paolo, Sergei, this is Sergei. I will ask you some very provocative question. Why Macro did not discover neutrino oscillations?
Oh, they didn't have the sense.
Well,
I mean, Macro had about 600 events at 98, and they gave a talk just before Kajita-san's talk.
well, I should, Francesco, do you want to answer yourself? But let me give you, I think in some sense, Macro also discovered neutrino oscillations. That's my point of view. I think it's, no, I mean, but this is just, if you look the statement about systematic errors and so on, of course the Super Kamiokande results I agree, is more convincing, has more structure, has more, so here I think for me the question is, to me the question of recognition of the discovery. You know, I'm a great admirer of Kajita-san. Actually, he invited me to Japan, and I had a wonderful experience there for 6 months. And I think it's a absolutely wonderfully deserved Nobel Prize. But I think how we are doing history, I think the merit of a discovery is in a sense broader. And I think a piece of the recognition of the discovery goes also to Francesco Ronga and his colleagues. And I think, well, this is my, as I said, in the history, the fact that 2 experiments, which were Baksan and IMB, were excluding oscillations looking at through-going muons. And Macro was the other, so 2 experiments. So it's one of the big pieces of the 1998 result of Super Kamiokande was also the through-going muons were distorted by oscillations. And the distortions by Macro and Super Kamiokande were comparable. So in that sense, you know, this was a piece of convincing results. So to me, you know, let me just say something very personal. I think there is the Nobel Prize. It's over evaluated in some sense. You know, there is science. There are. So sorry. I don't want. No, but seriously, when you do, you know, there are other contributions which remains valuable. Stated this, I think, and this actually was my last transparency. When you make the discovery of a new phenomenon, you know, you want a lot of evidence, and the evidence is structured. You know, we discussed. So you want to see features in L or zenith angle, in energy. So Super Kamiokande had a broad range in energy, as John said, and the ensemble of the results were striking. In fact, actually, I think people accepted nearly too slowly the evidence. You know, you look at the multi-jab events, you know, like this, and it was spectacular. So the events that the through-going muons it's a more subtle result. You see a distortion of the angular distribution. You have to believe that you have calculated the non-distorted distribution correctly. But the macro result is to me, seems, which is consistent with the Super Kamiokande result, is consistent with what has been established. So anyway, this is the thing. So there is a context in which, well,
But it was a posteriori, and in the early, it was only after a lot of stimulation that people began to investigate it in macro, is my recollection, talking to my friends at Caltech and Boston, that it was, they were following after the discovery had already been made.
Francesco.
So, well, that's fine.
It's mine? No?
Yes, please.
It's me. I just wanted to defend SU5 from your attack, Paolo. Because I was at the talk of Koshiba in Leipzig in 1984. He was jumping up and down on the scene like a real samurai, you know, and say, I'm going to find proton decay. That's why he built, you know, Kamioka.
Yeah.
That's why, because he was going to find proton decay. He was very fortunate that those neutrinos were traveling already for 160,000 years, and the detector was ready when the neutrinos arrived. So he was very lucky to find them, thanks to SU5, which said that the lifetime is 10 to the 39 years, and so there was a chance of finding it. So I think you should take back when you called it a failing, model SU5.
Well, look, it did a great thing for us. It did a great thing, but in IMB, when we eliminated the SU5 prediction, our friends at Harvard had already said that the model was not viable.
Well, I worked on it
that's okay.
for a few years, and what happens is that, of course, the gauge sector is just perfect. It's really very nice. It has baryon number violation,
Right.
everything is really beautiful, but we don't understand the mass sector. The
Yes, of
Higgses.
course.
There were so many Higgs.
And by the
there were
way,
so many things.
Super K got its money largely on proton decay, at least when I went to
I'm
the
glad to
high-level
hear
defense
that.
there.
Thank you. I'm very glad to hear that. So I think you should be very grateful to the
theorists have been very
so-called
good for us.
wrong but
But what have you done
interesting.
for us lately?
Me?
No,
Well-
the theorist community, to get us money to build big new detectors.
Excuse me, we're trying to tell you, but you don't listen. Okay, I'm a little bit exhausted by all of this. I think I want to go back to the Ray Davis. Yes? And by the way, yes, thank you for theorist. It's very good. We like it. So, number one, when the partial result came from Ray Davis, Willie Fowler said that, well, the sun has turned off. I thought I'd bring some levity. Secondly, I want to bring a story about, well, two stories about Ray Davis. One has to do more with his director, Maurice Goldhaber, who basically kind of saved the experiment by giving a pilot, allowing a pilot to go on. So it shows that you need to have a very good director, okay, not just somebody who pushes paper, but somebody who understands the potential of things. And secondly, this is a human interest story. Quite a few years ago, I was at some NSF thing, and I met somebody, a woman, chemist, who was born in Leeds. Leeds is the position, is a place where the homestake thing is. And she related the following story. She was a father was a miner in a mine, and women were not allowed in the mine except once a year. And for reasons like Liz Meitner was not allowed in the Kaiser Wilhelm Institute because her hair would catch fire on the Bunsen burner. The same kind of thing. And what happened is that she met this man who undoubtedly had to be Ray Davis, and they started talking. And he said, "What do you do?" "Well, she likes science and everything else." And then Ray told her, "Oh, but you know you can do much more than becoming a high school teacher." And she credits him. She did not know his name or anything like that, but that was an incredibly interesting story. And Ray Davis was a wonderful man, never talked about these things, never knew it, and I thought this is a place to talk about it. Thank you.
By the way, just interjecting, when we were first going to Kamiokanda, women were not allowed in the mine there at first. That was a revolution.
I'm Francesco Ronga, concerning Marco. I should say that indeed we had a strong discussion inside Marco, particularly with the Boston group. But at the end, the spokesmen, that Betty Parish and Giacomelli, decided to present our result that were in favor of oscillation at the Takayama conference just before the talk, the Kaijita talk. And if you see, there is a poster with the original slides, and the conclusion is that our result was in favor of oscillation at 3 sigma level. 3 sigma was not enough to claim a discovery, but the results were in agreement with Super Kamiokanda. In 2000, the 3 sigma, in 2000, we published a paper with the final result with 5 sigma evidence.
Okay, so...
Very short comment. No, I just wanted to say, because also see Alexei Smirnov here, the comment is that the potential of physics with atmospheric neutrino is not exhausted. And there are future experiments which have the potential of measure the hierarchy, potentially the delta phase, and Hyper Kamiokande has a wonderful program to do this science. And the potential of neutrino telescopes in this direction is really very interesting. Alexei has been developing calculation together with others, Zhenya, and I think we should not forget this, that the potential of atmospheric neutrino, the control, so some of these questions at higher level will happen. So I think this, for me, was important to make this comment.
So I just slip in one tiny thing. I don't think there's a talk here about the superluminal neutrinos, is there? No, I think it's a serious issue, and it's a beauty. That you're going to talk about it, Maury? Science in action. It's a great example. It worked. Yeah.
Okay, thank you very much for your beautiful talks, and thank you for all.